Any motion of charge from one region of a conductor to another constitutes current. When an isolated conductor is placed in an electrostatic field, the mobile charges in the conductor rearrange themselves so as to make the entire interior of the conductor a field-free region and its surface an equipotential surface. The motion of charges during this rearrangement is a temporary or transient current. To maintain a continuous current, we must maintain a steady force on the mobile charge in the conductor, either with an electrostatic field or by other means to be described later. The motion of a charged particle in a conductor is very different from the continuously accelerated motion that results when a constant field is applied to a charge in a vacuum. In a conductor, a charge bumps along randomly, accelerating until it collides with a stationary particle. The charged particle thus gives up some of its kinetic energy, accelerates again until it bumps into something else, and so on. Thus there is a lot of back and forth motion with a gradual drift in the direction of the electric field force. The inelastic collisions with the stationary charges transfer energy to them. This increases their vibrational energy and hence the temperature of the conductor. It is useful to consider the motion of charge in a conductor across or through some imaginary area. The area might be, for example, a cross-section of a wire used as a conductor. We define the current through an area as the net charge flowing through the area per unit time. Thus, if a net charge delta Q flows through an area in time delta T, the current through the area is I equals delta Q over delta T. It's the rate of flow of charge. This rate of flow of charge may vary with time. In that case, we generalize the definition of current in a natural way using the derivative. We define here the instantaneous current I as dq by dt. Now current is a scalar quantity. The SI unit is 1 coulomb per second, called 1 amp. The current through an area can be expressed in terms of the drift velocity v of the moving charges. Consider a portion of a conductor of cross-sectional area A, as shown here, through which there is an electric field E, which is shown here, directed from left to right. Suppose first that the conductor contains 3 positively charged particles. These move in the same direction as the field. A few positive particles are shown in the diagram here. As you can see, these are moving in the direction of the E field here. Suppose that there are n such particles per unit volume, all moving with a drift velocity v in a time delta t. Each particle advances a distance v delta t. Hence all the particles within the shaded cylinder of length v delta t, and only those particles, flow through the end of the cylinder during time delta t. The volume of the cylinder, so the volume of this cylinder, is A times the length, v delta t, and the number of particles within it is n time, because now remember n is the number of particles per unit volume, so if we put n in, so if we say the number of unit particles per unit volume times the volume, then we're going to get all the number of particles that are in this volume. I'll just repeat here. The volume of the cylinder is A v delta t, and the number of particles within it, as just described, is n a v delta t here. If each particle has a charge q, the charge delta q flowing through the end of the cylinder in time delta t is I here, I delta q over delta t, which obviously is, we divide through by delta t here, yeah, we're going to end up with nqv, so that's the number of particles per unit volume, and the charge times the charge on each particle times the speed times the area we're moving through. If the moving charges are negative rather than positive, the electric field force is opposite to the electric field, and the drift velocity is right to left, opposite to the direction shown in the diagram. but the current is still left to right. The reason is that negative charge moving right to left increases the positive charge at the right of the section, just as positive charge moving from left to right does. Thus the motion of both kinds of charge has the same effect, namely to increase positive charge at the right of the section. In both cases, particles flowing out through an end of the cylinder section are continuously replaced by particles flowing in through the opposite end. So in general, a conductor may contain several different kinds of charged particles, having charges Q1, Q2, Q3, N1, N2, N3, etc., and drift velocities V1, V2, V3. We can write it as the current density by dividing through that by A. So we get the current density is I over A, which is N1, Q1, V1. So then we have the current density, which is the current per unit meter squared. We can also define a vector current density that includes the directions of the drift velocities. So we can write the current density as a vector if we treat each of these velocities as vector quantities.